because when we do an or, if we have a mutually exclusive problem, we're going to have to subtract the part where they overlap. Otherwise, we're going to count them twice. So right now, we're just going to check through and see, are these mutually exclusive? Can they happen at the same time? Mutually exclusive means they cannot happen at the same time. This is really the only rule we have to worry about. So if I roll a die, I roll a 3 on a die, I roll a 4 on a die. Can they happen at the same time? No. Therefore, these guys are mutually exclusive. The word exclusive means excluding. They excluded each other. There's nothing that they can overlap with. Event A, randomly selecting a male student from a group. Event B, from the same group, randomly selecting a nursing major. Can that happen at the same time?
Yes.
Yes, I can have a male student who is in fact a nursing major, right? These are not mutually exclusive. They can happen at the same time. Everybody kind of seeing this? You don't really notice it until we start working with it. Randomly selecting a blood donor with type O blood and randomly selecting a female blood donor. Mutually exclusive?
No.
No, they can happen at the same time, right? Be careful the way you answer that. Mutually exclusive means they cannot happen at the same time. Exclusive, they exclude each other. Think of it that way. So think about this one for a second. Randomly select a jack from a standard deck of cards. Randomly select a face card from a standard deck of cards. Not mutually exclusive, because in my face cards is my jack. This says get a jack. This says, oh, there's a jack in here as well. So they are not mutually exclusive. Okay? Randomly selecting a vehicle that is a Ford and randomly selecting a vehicle that is a Toyota.
Mutually exclusive.
Mutually exclusive. I can't select one vehicle and have it be a Ford and a Toyota, right? So far, Ford and Toyota have never merged together. I take it? One day they might, but not today. Okay. Now, here's where the addition rule comes in. The addition rule we use for an or statement. The event that A or B will occur. So we write it like this. The probability of A or B is the probability of A by itself plus the probability of B by itself. And if they are mutually exclusive, that's all that will happen when they are mutually exclusive because they have no overlap, nothing in common. So we can take the probability of getting a Ford, we can take the probability of getting a Toyota, and figure out what is the probability of it being a Ford or a Toyota. That's mutually exclusive. If they are not mutually exclusive, such as the jacks and the cards, then we have to subtract out where they overlap. So for instance, the probability of getting a jack or a face card. What's my probability of getting a jack out of a deck of cards? 4 out of 52. Now, can these happen at the same time? Can I pull a jack, a face card that is a jack, in fact? What's my probability separated that is a face card? Just a face card. 12 out of 52. Now, the part that we subtract is where they overlap. How many of those face cards are jacks? 4. So we have to subtract out what we overlapped. And then just reduce it. The problem is this. If I laid out your deck of cards, and I said pick a jack or a face card, you would pick all your face cards, right? Because don't they contain your jacks? face cards, 12 face cards. Aren't your 4 jacks sitting right in there? So there's only 12 total things that you could get. Picture a deck of cards laid out in front of you, and I said, pick out all the jacks for the face cards. So you pick out all the jacks and then the rest of the face cards. Together you have 12 cards. You can't have 16 cards. That means you counted the jack twice. So this guy has a little bit of overlap. Is where the overlap is, we subtract out. Granted, this wasn't the greatest of examples, but I wanted to show you, because this one makes it so obvious, that it is. We counted them twice. If we counted jacks, and we counted all our face cards, the jacks are in both. Okay, normally you'll subtract out a few. So we'll take a look at this. You select a card from a deck. Find the probability that one card that you get is a 4 or an ace. You're only pulling out one card, a 4 or an ace. Okay. So how many 4s are these mutually exclusive? Can you pull out a 4 and an ace at the same time? Can that 4 also be an ace? No. So what we're saying is then that is the probability of a 4 plus the probability of an ace. So these increase your chances. Just think about it logically. If you're pulling out a 4 or an ace, I can get 4 aces or 4 4s. How many cards is that total? 8. I can get 8 out of 52. The probability of me getting one of those is 8 out of 52. The probability of A, 4 out of 52, plus the probability of B, 5 out of 52. In fractions, when we have the same denominators, we just add their numerators, which is when we get to the ors, which is why I say don't reduce, because you want your denominators to be the same. There's nothing in common between them. If we laid out all the deck, the probability of getting a 4 or an ace is the total 4s and the total aces put together, right? You roll a die. Find the probability of rolling a die less than 3 or an odd number. Here's your die. Okay. How many of those numbers are less than 3? 2. How many of those die are odd numbers? So, I have the probability of selecting a 1, a 2, a 3, or a 5, right? So what's that probability? 1, 2, 3, 4. 4 out of 6. So, probability of getting a number less than 3 or odd. What's the probability of a number less than 3? Okay, 2 out of 6. What's the probability of an odd number? 3 out of 6. And which one overlapped? Which one did I count twice? Because when you added those up, didn't you tell me that was 4 out of 6? If I added these would be 5 out of 6. I have to subtract the one that I added twice. This is the and condition. When it was an odd number and a number less than 3. This gives me my 4 out of 6, or my 2 out of 3. So do you see where that or has an overlap? That's the one we're looking for. Yes, the 2 out of 3. The thing is, don't reduce these as you go, because when you're adding fractions, you want to keep the same denominator. So don't reduce till the very end. This is a great example of seeing that they're not mutually exclusive. I can pull out a number that is less than 3 and is an odd number at the same time. So I can't count them in both of my sections. And when you're dealing with rolling a die, that's the best way to do it. Lay them out. You don't really even have to do the probability. You can just say, well, I counted this one already. This one, this one, this one. I got 4. 4 out of 6. Yes? All right, let's have you think this one out. Think out these two. Work these out. Take a minute, work them out. Whichever way you solved it.
So I did 1 out of 6 because the probability of rolling is 6 or 6 out of 5, 1 out of 6.
Good.
And then added. Divided.
Good.
Mutually exclusive.
They're mutually exclusive. Very good. Good. Second one, anybody want to do the second one? Jocelyn, go right ahead. Come up with the point. I'm good. How are you? That's all right. Yes, he is. Yeah, absolutely. What do you want? I'm glad to send him down later. I'll send him down. All right. Thank you. Bye. Well, someone wants to see you. Your coach. Yeah. Give you a pass. Ah, look at this. She found the mutually exclusive. Did you guys find the mutually exclusive?
Uh-oh. Well, come on. Should have been getting a good phone in the expecting it. Trying to hold it. You better be looking at this.
Probably will be back, he said. Okay, so selecting a card from a standard deck. Find the probability that it is a face card or it is a heart. Now, face cards there are 12 out of 52. Hearts there are 13, that's one suit out of 52. That's the time you don't want to write 1/4 because you're going to have to convert your denominator to add your fraction anyway. And how many of those hearts are face cards? 3 of them. So we're going to subtract out the 3. You added it in the face cards, you added it in the hearts. So together, 22 out of 52. And then at the end, you can reduce it. Does everybody see the mutual exclusive? Okay, this was very good, guys. Very good. Mutually exclusive is a tough one to get sometimes. Okay, and they do this with tables as well. The frequency distribution shows the volumes in sales, dollars, the number of months a sales representative reached each sale level during the past 3 years. If this sales pattern continues, what is the probability that the sales representative will sell between $75,000 and $124,999 next month? This is what's forecasting, what's predicting this. First of all, are these sales levels mutually exclusive? Can they happen at the same time? Okay, granted, he can earn $30,000, which puts him in between here and here, but they've separated them, so you can't earn what's in here and earn what's in here. You either earn one amount or you earn the other amount. Like, I realize 50,000 includes 30,000, but they're just looking at a sales level. So they're, according to our chart, they are mutually exclusive. So we want to go between 75,000 and 124.99. So we want to take these guys and add them up and put them where? So I get 16, I get 18. So is 18 my answer? It's a probability. So 18 out of what? Does it give us a total? It says, no, so what is my total, my grand total there? What is my grand total? 36?
Yes.
Okay, so you're going to add those up. They are mutually, oh, wait, was it 124? Or 149? 124, so 16, sorry about that. 16 out of 36. When you look at a chart like this, they're going to naturally be mutually exclusive. And usually that's what they'll ask between. If you want to find the probability, I got it. Find the probability that they will sell between 0 and 49.99. So that would be these three. Just these two. The 3 and the 5. 8 out of 36. This chart is meant to be at that level. So if you sold 50,000, yes, I realize you passed 30,000 mark, but they're looking at it in terms of levels. What level are you at? So that makes the levels mutually exclusive. Just remember to do the total. Because your probabilities always are between 0 and 1, which is a nice way to remember. If you add sometimes and you forget to subtract the overlap, you may be greater than 1. So in other words, if I did one that said this, and this is a good way to remember it, what is the probability of getting it even or a number less than 5? So here's my numbers. I've got 3 evens. A number less than 5. 1, 2, 3, 4. Can I possibly have a probability that is greater than 1? So this told me I forgot to subtract something. So where did they overlap? I had 2 overlaps here. I forgot to subtract my overlaps. Okay, so sometimes that's a good hint. Don't let your probabilities be more than 1. Something went wrong. And just as we did your givens and your other statements, we can do these guys too. I don't think I can fit them all on the same screen. Okay, a blood bank catalogs the types of blood, including positives and negative Rh factors, given by the donors for the last 5 days. The number of donors who gave each blood type is shown in the table. A donor is selected at random. Find the probability that the donor has a type O or a type A. Are they mutually exclusive? Can you have O and A at the same time? No. So they're mutually exclusive. So how many had type O? 184 out of what? 409. How many had type A? 164 out of 409. This is why you keep your denominators the same, and don't turn them into a fraction until the very end, because what happens with a fraction is you have to round. So keep them as a decimal. Don't turn them into a decimal until the very end. You have to round your decimals. So you'll, first of all, never convert back to a fraction if you round your decimals too soon. So leave them as fractions, unreduced, until the very end of everything that you add, subtract, or whatever you need to do to it. Otherwise, it's not going to work out. And this one works out to 348 over 4. Oops, 340. Oops, 164. Over 409. And then at the very end, reduce it to a decimal. If you reduce it to a decimal at the end, it also lets you compare the rest of them, unless you leave them all in the same denominator. Okay, I'm going to have to hold the book for this one. Find the probability that the donor has type B or is Rh negative. Are these mutually exclusive? No, they happen at the same time. Can you be a B and an Rh negative at the same time? So watch. Here's all my B's. This is the best way to show it. Here's all my Rh negatives. Ah, did they overlap? Where did they overlap? At the 8. So that's the one I counted in this column, and I counted in this row. That's the one I have to subtract. So the probability of a B is 45 out of 409, plus the probability of an Rh negative, 65 out of 409, but I counted the 8 twice. The charts are so much nicer to go through than like the card thing. It just makes life easier. This will give you 102 over 409. And if you want, convert it to a decimal. Okay, let's take a look at try it 4. I'm just going to erase this mess so we can draw again. Find the probability that the donor has a B or a type AB. And doesn't your chart help see that they are mutually exclusive? Where's your type A? Here. Oh, sorry, type B. Where's your AB? Do they overlap at all? No, they're mutually exclusive. So 1 and R, add them up. 45 over 409 plus 16 out of 409. See how your blood types get rarer? Your O is the most common, I guess. Then your A. Your AB negatives. There's your rarest one. So this comes out to be 61 over 409. And you guys do this last one. Oops. Sorry. The last one says, find the probability. Oh. All right. It's an O or RH positive. So see what you come up with for that. This is another good example of mutually exclusive. Or not. Anybody come up with an answer for me? John, you get an answer? David? Sarah? Everything calculated? Okay. $372 over 409. Everybody get that? Anybody get 528 over 409? Because 528 over 409 is greater than 1, right? Your probability of an O, 184 over 409. Your probability of a positive, 344 over 409. And this is going to be way, way, way too big. Those totals will be over 409. Will be over 1. Here's your overlap right here. See it? Where both of these cross. Minus 156 over 409. Good? I like the charts. I think they make it more visual for you. I like the Venn diagrams. I like the charts. The cards are a little harder to see. And then the last guy. You have to refer to your chart. Find the probability. You have a figure at the right-hand side on page 161. Also, at the top of 161, guys, that's a nice review thing. How to find them with words, how to find them with probabilities. I'll see if I can make a copy of that for you to keep in your notebooks. That's probably like sums up everything we've done up to now. So you're to figure at the right to find the probability that a randomly selected pick is not a running back or not a wide receiver. Okay. Is not a running back or a wide receiver. Now, if you want to sit there and count out all the other things that there are not, you can do that. But the other way to do it is using their complement case. Can you be a running back and a wide receiver at the same time in the NFL? No. So these are mutually exclusive. So if you want to sit there and count up everything else, be my guest, but you can do the probability of a running back or a wide receiver and subtract it from 1. That's its complement case. So much easier. And these are mutually exclusive. So find your running back. It gives you the top, you have 353 players. So you know your bottom number right away. So how many running backs are there? 21. And it tells you at the top, you got 253 players. How many wide receivers are there? 33. So nothing in common, so we're going to add these together. And we're going to use your complement case. So I don't really feel like adding up all those other ones just in case I miss them. I can, because it's right in front of me. I can just cross off my running backs, cross off my wide receivers, or I can just add my running backs, add my wide receivers, and subtract that from 253. Can I do it that way too? And then build my probability? Absolutely. You walked in right on our football question. We're looking at an NFL rookie chart on page 161. So now you have to find the probability that you are not a linebacker or a quarterback. They probably should have used nor, because it's not. So find the probability. Are those mutually exclusive? Can you be a linebacker and a quarterback at the same time? No. So I can also do the same thing. I can add up all of them but the linebackers and the quarterbacks. I can add up those two, subtract it from 253. Or I can take the probability of a linebacker plus the probability of a quarterback and subtract this whole thing from 1. There's a number of ways to write this. So what's your probability of a linebacker? How many linebackers? 30. How many quarterbacks? 11. So when you subtract these guys, add them and subtract them from 1, you get 212 out of 253. And you can reduce it or put it in a decimal. I don't think that can be reduced.
Those are mutually exclusive, right?
They are. They can't happen at the same time. And whenever you get a chart, you can tell easily